Hello friends, I am Professor D. Trivedi, going to take a second part of the unit separation of variables. That is, we are going to utilize this method of separation of variables over a spherical coordinate system. The first part we have studied with Cartesian coordinate system. Now, the question is this: when you can utilize the Cartesian coordinate system and when you can utilize the spherical coordinate system. Cartesian coordinate system means XYZ coordinate system. Variables are XYZ. And a spherical coordinate system means the variables are R, theta and phi will be there. So our main important question is this: when we can utilize the spherical coordinate system. Our motive is this: in some region of the space, we want to find out the solutions of the potential V. And for that, we should be given on a boundary which is enclosing that surfaces, which is enclosing that volume. Every surface's potential must be specified to you. That should be given to you. Then the solutions of the potential in that region of interest can be obtained either it is using the Cartesian coordinate system or using a spherical coordinate system. But for that, if the boundaries are plane, that means the surfaces which is enclosing our region of interest are plane, then we can go for Cartesian coordinate system. But if the region of our interest is surrounded by the curved surface or a round surface, then we should go for spherical coordinate system. Which is written here. You can see that spherical coordinates. In the example considered so far, Cartesian coordinates were clearly appropriate since the boundaries were plane. For round object, spherical coordinates are more natural. In spherical system, Laplace equation reads like this. What is the Laplace equation? Del square V is equal to 0. This Laplace equation, either in a Cartesian coordinate system or spherical coordinate system or a cylindrical coordinate system, we have to solve and we have to find out the potential which is a function of its variable, either xyz or r theta phi. In the example considered so far, okay, so this del square V is equal to 0, which is written in a spherical coordinate system like this. This is already derived with their coordinates 1 upon r square del r of r square del v upon del r. That is the first term which is depending upon r. Then the second term depending upon theta 1 upon r square sin theta del theta of sin theta del v upon del theta, and the third term plus 1 upon r square sin square theta del square v upon del phi square is equal to 0. I shall assume the problem has azimuthal symmetry so that V is independent of phi. In that case, the Laplace equation, which depends on the three variables r, theta and phi, is converted in a two-dimensional problem. That means the Laplace equation in two dimensions, it depends upon r and theta only. It is independent of phi, and that is called azimuthal symmetry. So in our problems, we are going to consider azimuthal symmetry and we will convert this Laplace equation in 3 dimensions to the Laplace equation in 2 dimensions. The third term, del square v upon del phi square, that is going to be 0. So this term is going to be cancelled out. Remains only first two terms. And the first two terms also, 1 upon r square is going to be common. So it can be taken out and r square is going to be multiplied this side, so that is also going to be cancelled out. So remaining without r square, this first term will be there. Del r of r square del v upon del r plus 1 upon sin theta del theta of sin theta del v upon del theta. This is equal to 0. This is your Laplace equation in a spherical coordinate system with azimuthal symmetry. Now, this is a partial differential equation. How to solve the partial differential equation? Again, we are going to utilize the method of separation of variables. That is, we can think a solution V is a function of r and theta, that is a product of functions, where each functions depend upon one variable only. Capital R is a function of small r and capital theta is a function of small theta. That way we can consider that our solutions V potential, which is a function of two coordinates r and theta, which is a product of two different functions where each functions depending upon one variable only. Substituting this in this equation, V is going to be replaced by r and theta here as well as here, and then we will be dividing by V. That means it is divided by r and theta. Then we'll get this equation. Let us see how it can be obtained. Let us say substitute here. V is equal to capital R, capital theta. Now capital theta is independent of r, so it is constant with this differentiation, so it will be taken outside. Capital theta is divided by V. V means r capital theta. So numerator and denominator, both the side capital theta is there, so that will be cancelled out. Remains 1 upon capital R. Then this differentiation, which is a partial differentiation, is converted into a ordinary differentiation, because here only the capital R which is depending upon small r. So that one function is remains. That's why d dr of r square d capital R upon dr. That is the way first term is going to be obtained. Similarly, the second term, V is substituted by r and theta. So here r is going to be common, which will be common outside because it is constant, it does not depend upon theta. And r upon r theta, so r will be cancelled out, 1 upon capital theta remains here, into sine theta, d d theta of sine theta, d capital theta upon d theta is equal to 0. So this way we have obtained the equation 3.56. Now in this equation, one thing you notice, the first term depends upon only one variable, that is small r. Second term depends upon another variable, that is going to be small theta. So first term we can write that is a function of small r only. Second term is another function, let us say g, which is a function of theta. So f r plus g theta, that is equal to 0. That way we can write. Again, we can apply the same logic, same strategy what we have studied in Cartesian coordinate system. That is fr plus g theta, that is equal to 0. This is only possible if both the functions f and g must be constant. So consider that the first term is a constant c1 and another term is going to be c2. So c1 plus c2 is equal to 0. This is the only way this equation can be satisfied. One of the constants should be positive, another constant will be negative. Definitely we are going to take the first term, that is c1 is going to be positive, c2 is going to be negative, and c2 is equal to minus c1. So here we can say that since the first term depends only on r and the second term depends only on theta, it follows that each must be constant. So 1 upon capital R d dr of r square d capital R upon dr, this is equal to constant c1, and that value of the constant we have choose arbitrarily like this, L into L plus 1. This is c1. And the second part, 1 upon capital theta sine theta d d theta of sine theta d capital theta upon d theta, that is equal to c2, and c2 is equal to minus c1, so it is equal to minus L into L plus 1, so it is a negative constant. Here L into L plus 1 is just a fancy way of writing the separation constant. You shall see in a minute why this is convenient. As always, separation of variables has converted into a partial differential equation 3.54 into ordinary differential equation 3.57. So we have seen that the previous equation, which was this 3.54, which was partial differential equation because V was depending upon two different coordinates r and theta. This is going to be converted into two different equations. In both the equations, the functions is depending upon one variable only, so it is converted from partial differential equation into two ordinary differential equations. Now, ordinary differential equations are a lot easier to solve compared to partial differential equation. So we have here utilized the method of separation of variables. Now, the first term, which is dependent upon small r, that is related with the distance. So this term is known as the radial equation. Second term is depending upon theta, that is angular position. So this equation is known as the angular equation. Now, how to solve this equation? This is second order differential equation, ordinary differential equations. So it can be integrated two times and you can get solutions of this radial equation. So radial equation, dr of r square, d capital R upon dr is equal to L into L plus 1, and this r is multiplied here. So L into L plus 1 into r will be there. That is equation 3.58. And this has a most general equation solution, and that can be obtained. Capital R is a function of small r, capital A r raised to L plus capital B upon r raised to L plus 1. This way, we get these general solutions of the radial equation. Here, you can see that what is A and B? They are constant of integration. Naturally, it is generated when you integrate two times. As you can check easily, A and B are two arbitrary constants to be expected in the solutions of a second order differential equation. But in an angular equation, that is the next equation, this d theta of sine theta, d capital theta upon d theta is equal to minus L into L plus 1 into sine theta, capital theta will be there. This is your angular equation is there. Here, this angular equation is not that easy to solve by taking double integrations, but it is found out by someone, and the solutions of this equation that we are going to take as it is. And that solution is capital theta is a function of small theta, that is equal to PL cos theta. What is PL cos theta? PL cos theta is nothing but Legendre polynomials in variable of cos theta. Normally, the variable is taken as x variable, and this different Legendre polynomials are solved, or they can be find out that different value using Rotax formula. So PLX is most conveniently defined by the Rotax formula. PLX is equal to 1 upon 2 raised to L into L factorial d dx of Lth order of x square minus 1 raised to L. This is your Rotax formula. In this Rotax formula, for different value of L, L is supposed to be starting from 0, 1, 2, 3, like that way. It is a positive integer. So, using this Rotax formula, different Legendre polynomials like P0x, P01x, P2x, P3x, P4x, P5x, etc. you can find out. You can evaluate substituting different value of L in these equations. How you can find out? Let us see. If you substitute L is equal to 0, 2 raised to 0 is going to be 1 into 0 factorial, that is going to be 1, d dx raised to 0, x square minus 1 raised to 0. So this all comes out to be 1 only. If you substitute L is equal to 1, then what happens? 2 raised to 1 is going to be 2. Here 1 factorial. So 1 upon 2 here will be there. d dx of 1, x square minus 1 raised to 1. So d dx of x square minus 1, that is equal to 2x, and here it is divided by 2, remains x. So P1x is equal to x. Similarly, we can substitute here. L is equal to 2, and then we can find out P2x. 2 raised to 2, that is going to be 4 into 2, that is going to be 8. 1 upon 8 will be there. d dx second order, x square minus 1 whole square. And if you solve this one, you will find out this value is equal to 3x square minus 1 whole divided by 2. So this way you can obtain the second order polynomials P2x. Now the third order polynomials, L is equal to 3. Substituting L is equal to 3, you will get P3x is equal to 5x cube minus 3x whole divided by 2. Similarly, substituting L is equal to 4, you will get fourth order polynomials P4x, that is equal to 35 x raised to 4 minus 30 x square plus 3 whole divided by 8, and P5x, that is equal to 63 x raised to 5 minus 70 x raised to cube plus 15 x whole divided by 8. So this way some few Legendre's polynomials are given over here. Why this table is there and what is the purpose for us? In future we are going to take some examples, and in examples we are going to utilize this Legendre's polynomials. This first few polynomials are required, and that's why we are going to utilize this polynomials to solve that examples. Notice that PLX is, and name suggests, is nth order polynomials in X. It contains only even powers if L is even, and it contains odd powers if L is odd. The factor in front, 1 upon 2 raised to L into L factorial, was chosen in order that PL of 1 is equal to 1. What does it mean? If you think about that, L is even number is there. That means L is equal to 0, L is equal to 2, L is equal to 4. Then in that expressions, if L is equal to 4, that is even number is there. That means the power of x is going to be 4, power of x is going to be 2, power of x is going to be x raised to 0. So here in this expression, power of x is going to be even only. If L is equal to 2, here the power of x raised to 2 into 1 into x raised to 0. So here also the power of x is going to be even only. Here also the power of x is going to be even only. So L is going to be even, then the power of x is going to be even only in that expression. If L is going to be even odd, L is equal to 1, L is equal to 3, L is equal to 5. Then what happens? X raised to 1, that is also odd. P3x, L is equal to 3. So x cube and 3x raised to 1. That means here in this expression also, the power of x is going to be odd only. P5x, here you see that x raised to 5, x raised to 3, x raised to 1. So it means in this expression also, the power of x is also going to be odd only. So this is the indication, this one. Now in this Rotax formula, this factor is chosen 1 upon 2 raised to L into L factorial. Why? Because for all Legendre's polynomials with variable is converted to 1. That means PL of 1, that is equal to, suppose value should be 1. So for that reasons, this factorial is placed for here. Now this Rotax formula obviously works only for non-negative integers value of L. Moreover, it provides us with only one solution. So one of the solutions is provided by Rotax formula, that is theta is function of theta, that is equal to PL cos theta, that is Legendre's polynomials in a variable of cos theta. But our equation, angular equation, is second order differential equation, and it should contain at least two independent solutions. So how we can obtain the second solution? Second solutions, we are not going to accept that second solution. The reason is this: one of the second solutions you can obtain for all value of L is equal to 0 is this, that is capital theta is a function of small theta, that is equal to log of tan theta by 2. But in this equation, if you substitute the value of theta is equal to 0 or value of theta is equal to theta pi, then what happens? Tan 0 or tan pi by 2, that is going to be, you can say that sine 0 upon cos 0, that is 0 upon 1, and log of 0 upon 1 is going to be undefined, or it is going to be blow up, and that is the reasons these solutions cannot be acceptable. So there is another solution, but that solutions we are not going to accept, and only one solution, that is Legendre's polynomial PLX, we are going to accept. and hence in the case of azimuthal symmetry, then the most general separable solutions to the Laplace equation consisting with the minimum physical requirement is V is a function of r and theta, that is the product of the two functions. Capital R is a function of r, and its solutions is this: a r raised to l plus b on r raised to l plus 1 into theta is a function of theta, and its solution is Legendre's polynomials where cos theta is there. So taking this product, we can find out a general solutions V r theta. Now, as previously, here we are not getting a single solution. We are getting a set of the solutions for each value of L. So L is equal to 0, there will be one solution. L is equal to 1, another solution. L is equal to 3, 3 is the third solution. So we are getting here the set of the solutions. And each of the solutions can satisfy the Laplace equation. So this is using the property of the completeness. We can say that if we take the linear combination of this all the solutions, that also can satisfy your Laplace equation in r theta coordinate system. And hence we can write a most general solutions of the linear combination of the separation solutions can be written as V is a function of r and theta is equal to sigma. L is varying from 0 to infinity, and A and B is now changed with the suffix AL r raised to L plus capital BL upon r raised to L plus 1 into PL cos theta. This is equation 3.65, and this is the most general solutions of this azimuthal symmetry with Laplace equation in spherical coordinate we can obtain. Thank you very much, friends.